Perfect.
Okay, great. Okay, thank you all for having me. I'm calling in from Austin, Texas, so kind of on the other side of the world. Okay, so I'm coming from a slightly different background than meshing. So when I started grad school, I was working in computational fabrication, where we were trying to weave structures to approximate an arbitrary shape. But this uses the kind of same surface parameterization pipeline that everyone has been talking about, except our goal was to actually make the things at the end. So I'm going to be talking about kind of the things that we were working on in this project, and also the things that I've been continuing to work on. So just as a brief summary, I'm going to be talking about integrability, as a number of other people have been talking about today. Specifically, I'm going to be talking about something called the Aviles-Giga functional, which I think is not something that people in this community think about too much. It's very similar to something that people do think about, which is the Ginzburg-Landau functional. And I want to kind of make an argument that the thing that we actually want to be minimizing when you solve a frame field problem is the Aviles-Giga functional, not the Ginzburg-Landau functional. And the difference is that there's an extra integrability constraint. And so minimizers of the Aviles-Giga functional have kind of a different qualitative behavior. You can have these sort of line domain wall singularities that appear in addition to just point singularities. And then I want to talk about the work that I've been doing with some other people on representing integrable polyvector fields. And I'm specifically going to be talking about it in 2D, but also I've been working in 3D. So there's several different problems in different domains that all kind of have a similar feel. So if you want to generate stripe patterns on surfaces, or you want to do remeshing, or you want to solve computational fabrication problems, you're using the same surface parameterization pipeline. So before I go forward, I'm going to be talking about the discretization that we specifically have been looking at, which is that for two manifolds, we're going to be thinking about unstructured triangle meshes. Scalar values will live on the vertices of our triangle mesh. The vector fields will live on the faces, or in 3D on the interior tets. So that's the discretization that we're using. And in this discretization, there's a paper by Poultier and Persus that gives in 2D an integrability condition, which is that if you have vectors that share, if you have two faces that share an edge, the projection of the vector field onto the shared edge must agree in order for the vector field to be integrable. And if your domain is simply connected, then this is actually a sufficient condition. So if this is true on every pair of neighboring faces, then your field is actually integrable. If your domain is not simply connected, then you have to deal with the extra degrees of freedom around the homology generators. And this definition also generalizes to higher dimensions. So on a TET mesh, now you have two integrability constraints per vector field per face, right? You want the projection now onto the common face to agree in order for the field to be integrable. Okay, so now I want to kind of present a bunch of different functionals that all kind of look the same if you write them down in a particular way. So if you have an integrability condition, you can write down the Hodge decomposition as we have a vector field W, and we're looking for the smallest delta that makes W plus delta integrable. And this is exactly this will give you the curl-free part of the Hodge decomposition. But there's other problems. So there's the Ginzburg-Landau problem, which is now you want a vector field which is everywhere close to unit and also smooth. So this is very similar to the globally optimal direction fields that you get. I know they're not exactly the same. Another energy is, suppose you have an input vector field. You want to search all possible rescalings of it to find the rescaling which makes it as close as possible to integrable. So this is very similar to a stripe pattern. So once you find this globally optimal rescaling, then you'll be able to integrate your vector field, and you'll get these nice evenly spaced stripe patterns. Right, and so then the thing that we were working on for the weaving project was we wanted a field that was everywhere integrable and everywhere close to unit and smooth. So now let's compare these two functionals. So Ginsburg-Landau says that you want approximately unit norm everywhere. In our weaving project, we also said that we wanted approximately unit norm everywhere. We also wanted the fields to be smooth. So the main difference is that in the Ginsburg-Landau energy, there's no integrability condition. Okay, so let's think about the Ginsburg-Landau functional for a second. So this is used in meshing. It's become more popular in the last few years. There's been a bunch of papers about using Ginsburg-Landau to do better meshing. And you find minimizers using MBO. So you do a diffusion, and then you project back onto the constraint, and then you do a diffusion and project back onto the constraint. There's this other thing called the the Aviles-Giga functional. It's really, you just replace every W plus delta with like a grad U. So now you've added a constraint that says that your vector field is actually integrable. And the minimizers of this functional have a qualitatively different behavior than the minimizers of the Ginsburg-Landau functional, which is kind of interesting, especially in the sharp limit. So as you let smoothness go to 0, you start getting these very kind of complicated domain walls that can form, which is kind of interesting. Maybe it's useful for meshing in some context. But the next thing that I want to talk about is how do you actually recover solutions, minimizers of this Aviles-Giga functional. And this is what we were doing in the weaving paper. So we're just going to do a little rewriting of the variables, right? So we're replacing grad W with grad U with W plus delta. And as you can see, it's almost the same. There's just like a square. If you look carefully, there's like a extra squared term, but other than that, it's basically the same functional. And if we look at the weaving formulation, then this is easy to minimize. And we also can recover these domain walls if we study the sharp limit. So if we set lambda very close to 0, then we can get these domains forming. What's more is we can set handle constraints and incompatible handle constraints. And then if we quench the smoothness down to 0, we get this fracturing behavior, which is also kind of nice. And furthermore, right before we set lambda to 0, we see that the delta term, so the place where the field is not unit, concentrates near these domain walls. So it's basically everywhere close to unit except on the domain walls. Okay, so then the next thing that I wanted to talk about is how do you numerically find solutions to this? Well, it turns out that if you write things in this form, then we can do an alternating minimization to first solve for delta, and it's a convex problem to solve for delta, the way that things are kind of written down. And then after you do a global solve for delta, then you do a local update everywhere to project back onto the unit constraint. So you want your vector field to be unit everywhere, and you just iterate. You do a global solve for delta, and then you project back onto the constraint. And at every step, you can show that the objective decreases. So this algorithm will converge. Okay, so this is kind of a pause point. So has that been clear? Are there any questions? Hello? Hello?
Yes, we are you. But
Oh, okay.
Question.
Okay. If there's no questions, I can continue. Okay. So,
maybe one very quick question. So far, everything was just about one vector filter, or did you also handle already some symmetry, like cross-field issues?
no, so this has all been just one vector field so far. So just going kind of slow. So the coming part will be multiple vector fields. And this follows kind of the algebraic representation kind of framework. So we're just going to be replacing a few parts of the minimization before, and basically the biggest change is that now instead of W being unit, W is now going to be something more complicated, so I'll get to it on this slide. So this is the reformulation of the functional from before. So we've replaced W with F, and in certain places we've added an extra lift. So we have an LF in places, but F is now going to be maybe a rosy, or maybe some sort of frame like a GL2 frame or a GL3 frame or an Odeco frame or an octahedral frame. It can be there's different varieties, but for the purposes of the presentation today, just for simplicity, you can think of F as a GL2 frame. And so, right, so it's just two vectors that are linearly independent. And so there's just a couple parts that change. So these are the three things that have changed. So we have to define what C is now and what L is now. So L is defined as just tensoring. So we're going to lift to the, so L, and then there's a on this slide, we're going to think of there being like a coefficient. So there's L2 and L4. So 2 will lift to the second order monomial basis, and then L4 will lift to the fourth order monomial basis. And we can add these together, right? So it makes sense to define L2, it makes sense to define L4, it makes sense to define the sum of two vectors that are lifted. It makes sense to define the sum of the L4 part with an L2 part, because these are just monomials. So we're just adding polynomials together when we do this. And so on the right here is a figure. You can think of this lift as, now you go from a vector, which you can think of as a linear functional, to some more complicated functional. So this is just plotting given the same input vector for different lifts, the sort of function from R2 to R that results. And specifically, we're restricted to a circle. So we're showing the value of this function on some circle of a fixed radius. So that's the lifting. So then we need integrability. So how do you define integrability? Well, in 2D, it turns out that this is pretty straightforward, because if we just, like, in the most general case, we take two vectors who agree in the x coordinate but have arbitrary y coordinate, we can see that there's always going to be one monomial term that doesn't see the y component. So if you're in L2, it'll be the x squared term. If you're in L4, it'll be the x to the fourth term. And so basically, for every L that you have, you'll be able to write down one integrability constraint. And so now if you want to do polyvectors, you can just lift to the sum of L2 and L4, and then you can impose a constraint on x squared and x to the fourth, and that'll give you two integrability constraints over the space of moments. So this will let you write down the GL2 integrability constraints. So here they are. It's a little bit more complicated than that because you're not always in such a convenient basis. So you have to also have to write down a rotation operator in the moment space that will let you express these constraints nicely. But basically the same framework that I presented earlier in this talk will still hold here, and you can still do a very similar optimization in the moment space by minimizing this modified function. And then there's, so the rotations are a bit complicated, but it turns out that because our lifting maps are either spherically or circularly symmetric, there's a connection to circular or spherical harmonics in that you can perform a linear change of basis from the moment space to the circular or spherical harmonic case, which lets you which basically lets you prove that these rotation operators must exist, and there must be a linear transform which gives you them. And so numerically, it's not too bad to do. And so we've implemented a 3D version of this, and we're starting to get some better results. So this is a very, very preliminary result, but this is one of these difficult hex meshing test cases, and we're showing two singularities of the right type that are kind of, it's doing basically what you want. The singularity structure isn't super smooth right now. We're still working on it, but this is kind of an early promising result. Okay, so that's what I had for this talk. Thank you for listening. If anyone has any questions.
Any questions? Comments?
There is one from Amir Waxman in the chat.
Oh.
So the question is, how do these terms relate to just polycurl?
Which terms?
The moment. Can you see the chat?
I have to exit screen sharing, I think. I can exit screen sharing.
Okay, so the terms are the moments.
Oh, I think it's pretty. This is the integrable polyvector approach. I think it's pretty similar. I mean, they're both representing polyvectors as polynomials. I think what's different is that the projection that we're using is different. I think I haven't talked about so right, like here we did with a single vector, the projection was just like normalize the vector per face. Now we need to project it. When we're doing this alternating minimization, we do a global solve for delta. The integrability constraints are linear, so the delta solve is still just you solve a linearly constrained quadratic program. But now the projection where you update the frame is different, and I think the approach for updating the frame that we're using is different than the one that is used in the polyvector paper.